Okay, this is Mr. Asher, and this is for Chem 121, and I'm going to finish up the questions I didn't do in class, and I have in my notes that I didn't get to 13, 14, 15, and 16. It might just been 14, 15, and 16, but I'm going to do 13 as well. Anyway, so we're trying to use chemical equations to do stoichiometric calculations. And the reaction I'm working with problem 13 is I have 2 benzene, which is C6H6, plus 15 oxygen molecules goes to 12 CO2 plus 6H2O. And this is the balanced chemical equation. And the problem 13 says, how many molecules of C6H6 are needed to react completely with 300 molecules of oxygen? So I have 300 molecules of oxygen. And I want to know how many molecules of benzene I need to be able to react with that. And the thing is, these stoichiometric coefficients here sort of have units associated with them. So the way we read this is 2 molecules of benzene, C6H6, react with 15 molecules of O2 to produce 12 molecules of CO2, right? So that means that they work sort of like unit conversions, and I can come up with a conversion factor here that would be molecules of C6H6 over molecules of O2. And then that's going to give me, once I solve all that and figure out what these coefficients are, then that will give me molecules of C6H6, because molecules of O2 will cancel. And the coefficients I need are 2 and then 15, right? Because it's 2 molecules of CO2, 2 molecules of C6H6 and 15 molecules of O2. And so that's going to give me molecules of that. Well, this becomes 600 divided by 15 molecules of C6H6, which is equal to 40 molecules of C6H6. So 40 molecules of C6H6 will react with 300 molecules of O2, and that'll consume both of them. And now the second part says how many molecules of CO2 are produced. Well, I'm going to base it off of molecules of CO2, molecules of C6H6, and so that would be 40 molecules of C6H6 times, and then I'm going to have molecules of CO2 divided by molecules of C6H6, and this is 12 divided by 2, which is 6. So 12 divided by 2 is 6, so this reduces to 6, and 6 times 40 is 240 molecules of CO2. Right. So that's how you do 13. I think I might have done that in class, but it doesn't hurt to review it. All right, and the next one, problem 14, talks about limiting reagents and how we use stoichiometric coefficients to figure out things like that. So same equation, 2C6H6 plus 15O2. It's still going to go to 12 CO2 plus 6H2O. And it says if I have 250 molecules of C6H6 and I have 2,700 molecules of O2, which will be the limiting reagent, meaning which one will I consume first? So one of these, unless they're in stoichiometric balance, will get used up. And remember, for each 2 of these, I have to use up 15 O2s. So I'm trying to figure out the stoichiometric balance of all this. Now, the thing is, you can think of this reaction, sort of this chemical equation, sort of like a recipe. And to each batch I want to make, I need 2 C6H6 and 15 O2s. And for each batch I make, 12 CO2s and 6 H2Os. So that means if I divide each one of these numbers by the stoichiometric coefficient, and this would be 2 molecules of C6H6 now sort of per cycle of the reaction, and this would be 2702 divided by 15 O2 per cycle, right? So for each cycle of that reaction, then when I do that division, I'm going to get 125 cycles of the reaction. So with 250 C6H6, with 250 C6H6 molecules, assuming I have enough oxygen, I can run the reaction 125 times. Now over here, if I have 2,700 CO2s, 2,700 oxygen divided by 15, this will run the reaction 180 cycles. And the limiting reagent is the one that's there that's the minimum. See, I can only run the reaction 125 times with 250 C6H6, but if I had enough C6H6, I could run it 180 times with this. So the minimum is limiting, and in this case, it's C6H6. Right? So that's how you do limiting reagents, right? So you divide through the stoichiometric coefficient, and that tells you how many times you could run that reaction, assuming you had enough of all the other reactants. And if there's more than two, it's fine. You just divide through each one you've got by the stoichiometric coefficient of that reactant. And again, it's whichever is the minimum, that's the limiting reagent. And then if you need to predict how much product would be formed, you base it off the minimum. So if we wanted to know how much CO2 was formed, we would have 125 reaction cycles times 12 CO2 per cycle. And that would give me, because I can't do that in my head, 125 times 12. That would give me 1,500 CO2 molecules. Okay. So it's all about reaction cycles when we talk about limiting reagents. Okay. All right. So next is 15. Sorry, I have to scan down to 15. All right. So now we're reacting magnesium. So 15 talks about the reaction of magnesium, which is Mg plus 2HNO3. And that goes to MgNO3 2, so magnesium nitrate plus a hydrogen gas. And I have 134.400 grams of magnesium, and it reacts with 1075.000 grams of nitric acid. And I produce 820.130 grams of magnesium nitrate and 11.148 grams of hydrogen. And it says, were the reactants completely consumed? And if they were, if they were, then the mass of reactants is equal to mass of products. In other words, 134.400 grams plus 1075.000 grams would equal 820.130 plus 11.148 grams. Clearly, that's not true. This is going to come out to be well over 1,200 grams. This is not even 900 grams. So clearly, there are more reactants. Sorry, I'm having trouble writing on the bottom of my tablet here. More reactants mass than product mass. So the reactants weren't completely consumed. Now we have no way of knowing which one of these reactants here at this point was there in excess and which was limiting. We just know that they weren't all consumed, right? Because this is going to be what, 1209.4. So this would be 1209.400 grams total of reactants. And over here, we've made 831.278 grams of product, right? So there's a missing mass there of over 270 grams or something, or 370 grams. So there's a lot of product, there's a lot of mass missing, and it's left in one of these two. And just because it's so much, you can figure out it's got to be in the nitric acid because we didn't start with, more than. So this all had to be consumed, and we had left nitric acid. We have to have nitric acid left over. But anyway, so one of them was limiting reagent. It was probably magnesium. All right, so same problem, same equation. Whoops, Mg. This is problem 16 now, and this will finish this off. Oh, plenty of time. Plus 2HNO3 goes to Mg. NO3, 2, magnesium nitrate plus hydrogen gas. And I have 1,451 atoms of magnesium, and it's going to react with 4,300 molecules of HNO3. And will it be Mg atoms? So which is limiting? And if we find out that, then we can find out which one, find which is remaining, right? Because the limiting one is completely consumed. It's the one that gets all consumed. And then the one that's in excess is the one that has stuff left over, right? So we're going to do the same trick we did before. And we're going to take 1,451 atoms of magnesium divided by 1 atom per cycle, which is sort of trivial. So with 1,451 atoms, we can run the reaction 1,451 cycles, assuming we had enough HNO3. And 4,300 HNO3 molecules divided by 2 HNO3 per cycle, and that comes out to be 2150 cycles, right? Okay, because 4,300 divided by 2 is 2150. So that means this is limiting, and that means limiting, and this is excess, which means HNO3 molecules remain, right? And then we can figure out how many are remaining by figuring out that we're going to run the reaction 1451 cycles because that's limiting. So the molecules of HNO3 required is going to equal 1451 cycles times 2 HNO3 per cycle, which is 2902 HNO3. So that means molecules of HNO3 remain are the amount we started with, which is 4,300, minus the amount we consumed, which is 2902, which is equal to 1398. 1290, 1398, 3, yeah, 1398. I think that's right. I suppose I should make sure I did my subtraction right. 2902. Yeah, 1398. Yay, I can add the subtract. Assuming I did this right, but that's right. 2 times 1451 is 2902. Okay, so 1393 HNO3 molecules remain. And then how many H2 molecules are produced? Okay, well, how many molecules, what's the stoichiometric ratio between magnesium and hydrogen? One magnesium produces one hydrogen. So if we consumed 1,451 atoms of magnesium, this was completely consumed, right? That means we make 1,451 molecules of H2, right? And to write that out, just so you have that, it would be molecules of H2 is equal to 1,451, atoms, uh, atoms of magnesium times one molecule of H2 over one molecule or atom of magnesium, right? So atoms of magnesium cancel. 1 times 1 divided by 1 is 1,451 molecules of H2. Okay. All right, so that finishes off that problem set. So you have all the solutions, and we'll move on to module 5 on Thursday. All right, I will talk to you later, and I'm going to stop now.